Hello there. Welcome to our today's science lesson. The topic for today being particles in elements and compounds, and the subtopic being doing more about the metals and nonmetals. In our previous lesson, we did so much on describing the so many elements we have in the periodic table, which we said there are 118 elements, 92 being naturally occurring. We looked at the elements in terms of how they occur, at what percentage do they occur in the Earth's crust, looked at some uses, and we even did some exercise on tabulating them in a bar graph to show how much is a particular element. And in looking at how they occur, we also did that and discovered that most of these elements do not really occur as pure elements, but they will always occur as compounds with other elements. Now, for today, we want to look at a little bit more about some of these elements in terms of the characteristics they show. I will start with the metals, then later on we look at the nonmetals. Metals, these are some of the common substances you must be interacting with oftenly. Probably where you are seated on a chair which is made up of a metal. The metal can be maybe iron or another metal. Probably you are also seated next to something that is electronic, and if you open up the electronic device, you may find a wire or two. What is that wire? That wire is a metal, and most likely it is made up of copper metal. So today we want to look at some of the metals. Maybe some we have already covered. We only do some extra explanation or description of the same, though some may be new ones. Now, looking at metals, generally these are substances that occur as solids. They are solids at room temperature. Most of the metals are solids at room temperature. However, out of these metals, we have one that is unique. In our previous lesson, I once mentioned that this element is called mercury. I'm now going to be using chemical symbols because most of these metals we have already talked about their names and their symbols on how they are supposed to be written symbolically. So I will be using symbols to name or describe the elements. So this unique element is mercury, which exists as a liquid. It is a liquid at room temperature. Because of that property, it is normally used in various uses, one of it being making of thermometers, such that when you increase the temperature, it increases in size, and by increasing in size, it fills up the thread where it is calibrated to show how much change in temperature one is talking about. So this is the only metal that exists in a different state of matter other than solid. It exists in the liquid state, while the others exist in solid state. Now, the other characteristic metals show are when you have a piece of metal. Now we have talked about they are mainly solids, and you freshly cut a piece of metal, assume it has been cut, you'll find that the new surfaces that will be seen, exposed will have a particular characteristic. They will be shiny. So this surface that is fresh will be shiny, and may also appear silvery, shiny, and some may also appear silvery. But all in all, we can see they are shiny. However, we have two metals that will not show the same. And these two metals are gold and copper. Gold and copper. So copper here, when you cut a new surface, it does not appear very different from the previous surface as it was. It appears copperish. We describe that appearance as copperish because there is no any other metal that will show the same appearance. And for gold, it is normally described as a goldenish or goldish because again, just like copper, it is only gold that will give that type of appearance. However, for the others, sodium, potassium, calcium, iron, any new surface, if it is cut, then it will appear shiny and probably silvery. Now, the other characteristic of metals is in terms of electric current and heat. Electric current and heat energy. If you look at heat energy, then we are also talking about electric current. You realize that if at one time you are holding maybe a piece of iron metal, maybe a nail, through trial and error, you didn't know what you are doing, and you place it on a flame. After some time, you will find that your fingers are being uncomfortable to hold the nail further. Or even if it's a spoon, a metallic spoon, the whole of it, if it is made of a metal, not having a plastic handle or another material. After some time, that spoon will be uncomfortable to handle. Probably you are cooking and using a spoon to turn your food. When starting, the spoon is comfortable to handle, but with the time, the spoon becomes unbearable. It is very hot. What has happened? Whatever has happened is there is a transfer of heat from one point to another. That shows that the material is conducting heat energy. What does this then show? It shows that metals are good conductors of heat energy. That's why that spoon of yours or whatever material you are using to turn the food in that sufuria, which was made of metal, as you are turning, this part became more hot. This region became more hot because it is directly in contact with the food. The heat energy then started moving upwards towards this side where you are handling. So by the time it reaches at this point, it shows that whatever is in between here must be a good conductor of heat energy, and that only works if the material is made of a metal. To maybe protect people from that, that's why you will find that some of the such implements in the kitchen are usually coated. You can coat it with a material that does not conduct heat energy. So metals are good conductors of heat energy. The other thing that requires conductivity is electrical current, electricity. Metals are the ones that are usually used all over the world to complete circuits. You want to do electrification in a house, You will not go for any other thing other than a metal. Maybe the only thing you will do is choosing the type of metal. And here, by saying choosing the type of metal, I mean the type of wire. Because even if all metals are good conductors of electric current, there are those that are better than others. And also, you have to look at other characteristics, properties of that material, and also other related qualities. For example, weight of the metal. Even if iron is a good conductor of heat, and copper is a good conductor of heat, iron being too heavy, it will not be a preferred choice in making a wire, but copper will be. The other thing can be in terms of price. Maybe a metal like aluminium is light enough than copper, but looking at the price, copper is relatively cheaper than aluminium. So you'll find that because of the expense part of it, copper becomes a better choice. So depending on your way of analyzing the situation, any metal can do, but you will prefer according to your point of locality and how available the metal is. So all metals are good conductors of electric current. So in addition, we therefore conclude that metals conduct both heat, energy, and electrical energy. However, we also have some nonmetals. We have an nonmetal that is a bit unique, and it has to be mentioned at this point. And this one is carbon. As much as we have said that metals are good conductors of an electric current, we also have an element by the name carbon, which forms a substance by the name graphite that is a good conductor of an electric current, making the only nonmetal that is well known to be a good conductor of an electric current. Maybe one can ask, how come carbon, a nonmetal, as graphite, is conducting an electric current? The answer to this lies in the connectivity of the carbon atoms to form graphite. Remember, we say that all the things we have on Earth, however good, bad, shapeless, shapeful, whichever way, are being seen, they all go down to one thing. How are the atoms connected to form compounds? How are those elements connected to form those compounds? So, when forming this compound by the name graphite, compound because it is a connection of so many carbon atoms to form one single substance by the name graphite, the connectivity is what makes one of an electron, out of the 4 valence electrons in carbon, one of the electron is left free. And since it is free, it is able to move around in what we call a delocalized electron, making it possible for graphite to conduct an electric current. So that is about conductivity of an electric current. Now the other way we can describe metals is in terms of melting point. Melting point. Remember, we say that most metals are solid in state, solids. So we start with the melting. If you start heating a metal, if at all it will have to change its state, then it will mean it will be changing from solid to liquid. Now metals have relatively very high melting points. They have very high melting points. Why? This goes down to forces that holds the particles of the metals in that metal to form that metal bar. Each metal has its atoms in it, closely packed together, as we described solids in kinetic theory of matter, that solids are closely, have their small particles closely packed together, vibrating in fixed position. Now, if this is the state of the atoms making up that particular metal, the forces holding the particles may vary from one metal to another, because all these metals are not the same. However, even if the forces will be varying, that is to give the different properties each metal gives, all in all, their melting point will be higher than other substances. Now, if their melting point is this high, how about the boiling point? If they are to boil, then still the same applies. A lot of heat energy will be required, so making their also boiling point to be very high. But we rarely talk about boiling points of metals. We commonly talk about melting points of metals, because for you to shape some of these metals, they are usually first of all melted. You get the melt of the metal, then pour it in particular shapes so that it can be shaped in whatever item or shape one may need. So we don't talk about the gas that much, but it is there. The force holding the particles here is called metallic bond. The bond or the force that holds the atoms, the metallic atoms together, is called metallic bond, and it varies in strength from one metal to another. The other description we can use to describe metals is in terms of what you can do on a metal by using some bit of force, hammering, hitting. You can hammer a shapeless piece of metal until you come up with a particular shape. You can either make, maybe you had something like this, you hammer this until it becomes something flat, a sheet. You can as well do it by making a rod out of it. You have made a rod out of it. So this one is a rod and this one is a sheet. Then how do we call this? This is what we say, or what we call, metals are ductile and malleable. They can be shaped into sheets and rods through hammering. How does this one happen? When you look at this diagram showing the small particles in a metal, that is the atoms, when you are hammering, you are only but displacing these atoms from one place to another. So if I hit at this point, I'm trying to push this particle to this point. If I also hit this one facing that direction, I will push this one to this, and this one that was here, maybe it will be pushed further down. So if this one continues, hit the whole top layer, then even follow the second layer, you will end up now with such a thing. Only one layer because of the displacement. So it's just like marbles arranged in a container. Then you start lowering the walls of the marbles, that container that is holding the marbles. As you lower the walls, you expand the container, or if it's a box, you expand the box but lower the height. What will happen is the marbles will be rolling. So assume the rolling does not mean that now metals are, the metallic particles are mobile. As we were describing in the kinetic theory of matter, we said that the particles vibrate in fixed position. But here they are being forced by hammering to move. So we don't call it movement, but this one we call it shaping. So they can be shaped. So what we are seeing here is shaping. Shaping of metals, but not movement of the particles in that metal. So this description is called being malleable and ductile, being able to be shaped into sheath and rods. The last bit of description we can use to describe metals is the name. This one does not apply to all metallic names, but it applies to a good number of them. And this is in terms of how they are named, the name. Looking at the last letter of the name, a good number of them end up in UM. Take an example of any of the elements we have been talking about in our previous lessons. Yes, I'm sure you have remembered some. Write down their names. I'm sure you have done it. You have done it. Now look at the names. You find that a good number of them are ending up in UM. Let's look at an example here. If you look at sodium, UM, and this is what I'm talking about, the last two letters of the element. So we have so many of them. Can have platinum. These are new element. I have not mentioned this previously, but looking at the name, platinum, potassium, it will still end up in calcium, it will still end up in magnesium, it will still end up in So you can still try to identify metals by the way they are named. However, this is not the best method, because not all metals end up in the same. A good example is an element I've mentioned so much, and that is the copper. If you look at copper, it does not end in UM. Look at iron. Iron also does not end up with the UM in the name. So that is not the best way to identify metals. Another reason is we also have some nonmetals that end up in UM and yet they are not metals. And a good example of nonmetals that have the same way of ending but they are not metals is helium. Helium ends up in UM and yet it is not a metal. Selenium is another good example, ending up in UM. So because of these two situations whereby some metals do not end up in UM, while some nonmetals end up in UM, it disqualifies use of name as a method of identifying or characterizing a substance as a metal. You can use conductivity, malleability, ductility, luster, is it shiny when freshly cut, melting point, and so on. But naming is not a very good way of identifying metals. That's so much we have covered on metals. What about nonmetals? In the same spirit of going step by step, starting with the state at which some of these nonmetals occur, just like as we said, for metals, they are mainly in solid state, apart from one which is mercury. For nonmetals, they are mostly in gaseous state. So nanometals are mostly in gas state. Picking a good example is oxygen. Oxygen is a metal, a nanometal, and it occurs as oxygen gas. Nitrogen gas, nanometal occurring as a gas. Look at carbon dioxide. Still, all of these are gases, and they are nanometals. So most of the nanometals occur as gases. However, we also have others that exist in liquid state, which is only one. In a liquid state, we only have one example here, and that is bromine. So we have bromine. Bromine is a good example of nanometals that occur in a liquid state, brown in color. So the liquid is brown in color, but at room temperature it will always be seen to be a liquid. However, we also have others that exist in solid state, a good number of them, though not as many as the ones that exist in a gaseous state. And when they occur in solid state, some of them will have different colors. They will have different colors, and the different colors is because of connectivity. One of it being carbon. If you look at carbon, it is black in color, and it exists as a solid at room temperature. We just talked about graphite when we were describing nanometals that conduct an electric current. You cannot talk about it when it is in gas state, but we best describe it in solid state, and in that solid state is when it is used as a conductor, but it is black in color. So carbon, which is black in color. We also have another one by the name sulfur. Sulfur is yellow in color. Remember, all of these are solids. We also have iodine. Iodine is black in color, and iodine and silicon are two nanometals that have a bit of unique character. They show some luster of a metal, and yet they are not metals. They are black in color, but when freshly cut, or when a surface is freshly exposed to the atmosphere, it will show some characteristics of a metal by appearance, and yet they are not metals. However, their color is black. Another element we can talk about is phosphorus. Phosphorus has three colors depending on the connectivity, depending on the oxidation number of sulfur that is being used to form that sulfur. So we have white phosphorus, we have yellow phosphorus, and we have red phosphorus. So depending on the connectivity, phosphorus can give us all that in terms of connectivity. That's the much we can talk about in terms of states of matter, states simple of this matter in nanometals, where we have seen a majority of them occurring as gases, but at least we have one occurring as a liquid, that's the bromine, brown liquid, but some also are found in solid state as listed here. We can also describe the nanometals in terms of conductivity. Remember, we talked about conductivity in metals, so we can look at conductivity of heat and energy and electric current. Conductivity of heat energy and the conductivity of electric current. For nanometals, they don't conduct heat energy. Nanometals do not conduct heat energy, and that's why you will comfortably have a bonfire somewhere, big fire. But unless there is convection currents bringing in the heat energy closer to you, you will never feel the heat reaching you. When you get that heat coming to you, it's not that the oxygen gas, the nitrogen gas, the carbon dioxide gas in the atmosphere is conducting the heat. No. It will just be because of the convection current of air currents. That air is circulating, so as it circulates, it comes closer to you when hot, but does not mean that the nanometals, which are the gases, are conducting that heat energy. The same is seen for electric current. Nanometals do not conduct electric current. You can imagine at that place you are seated. Probably there is a fluorescent bulb or a bulb nearby you, meaning that electricity is just with you. If nanometals were conducting, would you be safe? Will we be safe? No, because the oxygen, the nitrogen gases, the CO2 will have conducted the electric current and we should all be electrified. But lucky we cannot be electrified because nanometals do not conduct electric current. However, we have one unique one, as I mentioned earlier, and that is carbon in the name of graphite. Due to the connectivity of the carbon atoms in the structure, one electron is usually left out free, which is delocalized, and in the process it conducts an electric current. Maybe just a rough way of showing how the connectivity is. To form a graphite shape, you can continue up to any point you want. Now at each point, these are carbon atoms. These are carbon atoms. And as you can see, at each point, only 3 electrons per carbon atom are being used to form the 3 bonds. But looking at the electronic configuration of carbon, which is 2, 4, it gives us 4 electrons in the outermost energy level, which is supposed to be used in forming the bond. This bond is normally called covalent bond. So 4 are supposed to be used, but here we have 3 covalent bonds, meaning that 1 is at this point, 2, 3. Where is the other one? The other one is left at every point. There is 1 electron left hanging. So it is this electron that is left hanging that is always in motion in the whole structure, in what we call the electron is delocalized, making graphite to be able to conduct an electric current. So graphite is the only nanometal that conducts an electric current. Otherwise, in general, nanometals do not conduct both heat and electric current. The other way we can describe the nanometals is in terms of melting and boiling points. Here we can talk about both melting and boiling points, because you can see that those that we saw, they exist in solid state like sulfur. We also looked at those that exist in liquid state, bromine, and those that exist in gas state like oxygen. So you can comfortably start from melting point. So in melting points, nanometals have lower melting points. They are not as high as that seen in metals. Why? This is because even if they are in solid state, just like metals, the forces that hold the particles vary in strength. For nanometals, the force that holds particles close by is called van der Waals force. this force that is holding these particles together or close by is called van der Waals force. Van der Waals force is a very weak force. But we can talk about stronger van der Waals force or a weaker van der Waals force. Just like if you are a sports person, an athlete, you can talk of a weak team and a weaker team. This team can be beaten by team A. And even this team C can also be beaten by team A. But comparing now B and C, you see, you have said B can be beaten by A. C can also be beaten by A, meaning that B and C are weak. But of these two, you can still come down and say, oh no, but B is, I think it can be beaten by C. Even if they are weaker to be beaten by A, but B can be beaten by C. So what does it mean? It means that B and C are weaker teams, or they are weak teams. But B is weaker than C. So the same applies to this. For metals, we talked of the strong metallic bond being the force that holds the particles together, making it hard to break, and therefore you require very high heat energy to acquire that melting point. For nanometals, the forces that are holding the particles together are relatively weak, what we call van der Waals forces. Van der Waals forces. So these van der Waals forces vary in strength depending on the size of the particle. The bigger the particle, the stronger the van der Waals force. Not strong, stronger, because this is comparative. You call it strong, then it becomes wrong, because we'll be talking about the strong bonds like covalent bond and metallic bond. But since you are still talking about this weak bond, you only compare it by saying stronger van der Waals forces. So for these that are existing in solid state like sulfur, iodine, they have stronger van der Waals forces between the particles. Let's take an example of these halogens. Halogens here, we are talking about iodine. Iodine, we have said it exists in solid state, followed by bromine, which exists in liquid state. Then we have chlorine. We have chlorine, which exists in gas state. And yet they are all halogens. These are group 7 elements. Why the difference in the occurrence in terms of states at room temperature? The answer lies in the size. Iodine is a bigger atom. So being a bigger atom, to make a molecule, that is two iodine molecules to come together, it will form a bigger molecule by size. If I can use this to describe, if I can have this as iodine, then I have this one for bromine and I have this for chlorine. You can see this one is bigger than the others and this one is the smallest. So if this is one molecule and I have another iodine molecule, another bromine molecule and another chlorine molecule, the attraction force between iodine will be stronger. So we can say stronger van der Waals forces, followed by between bromine and lastly between chlorine. Though we also have fluorine, which also exists as a gas. But to give the difference between chlorine and fluorine, you look at the melting and boiling temperatures. That of chlorine will be higher than fluorine because fluorine will be much smaller, also having an attraction between the molecules. So for nanometals, you look at the size of the particles, it's the one that gives the difference, having stronger or weaker forces that holds the particles together. So what is this one giving us? It is telling us that the melting and boiling temperatures of nanometals varies greatly, from relatively high for those that are existing in solid state to very low for those that exist in a gaseous state. You can remember the case of nitrogen gas, where we said that it goes up to negative 196 degrees centigrade. That is very low. So that is all about boiling points of non-metals. We can also complete our statement in relation, just like in metals, in relation to non-metals in terms of names. Don't use names to identify metals and non-metals. Just as I said earlier, metals end up with the UM, a good number of them, but it's not a guarantee always that any that has a UM is a metal, because we saw helium and selenium giving a contradiction. And also, we cannot just say those that are missing UM are non-metals, because we also saw metals like copper and iron, which do not end up with the UM being metals, and in fact, commonly used metals. In our general life, you will always interact with these metals and non-metals either as different shapes, different colors, different textures, different so many things. Don't always be deceived by how a substance look. Go further and do further analysis, observation, identification of the substance to know whether the substance is either metal or a non-metal. We have talked so much about the metals and non-metals from the previous topic, today's lesson, and now just to see how much you can give out of what you have been getting from the lesson, let's try to answer the following questions. Question 1, I will expect you to fill a table giving the properties of metals and non-metals. So we shall have a table, T table, and we look at the properties of metals, and here we can have non-metals. Now remember, it is always good when you are working on a T table that is comparing properties of whatever thing of any kind. Always use the same concept, property, idea of comparison to the two of them. If you are talking about, for example, melting temperature, number one, we can talk about melting and boiling points. If this is the point of interest you want to look at, what can you say about melting and boiling point in terms of metals and in terms of non-metals? So we can say, point number one, we can say metals have higher melting and boiling points. Non-metals have lower and greatly varying melting and boiling point. They have non-metals, they have lower, that is one, but remember they also varied so much. We have those that exist in a solid state, one existing in the liquid state, and a majority existing in the gas state. So they have lower melting and boiling points and greatly varying. That is to do with the melting point. Second point is in terms of conductivity of an electric current. In terms of electric current conductivity, which always goes hand in hand with the conductivity of heat energy, metals conduct heat energy, they also conduct electric energy. Can as well split, talk about heat energy, that metals conduct heat energy, non-metals do not conduct heat energy. Metals conduct electric energy, non-metals do not conduct electric energy. However, carbon conducts electric energy. And to be more specific, it is carbon as graphite, because even diamond is carbon and diamond does not conduct. So in describing that nanometal as a conductor, you have to be a bit specific by saying carbon as graphite conducts electric energy. You can also talk about shaping. If you look at shaping, metals can be shaped. That is, they are ductile and malleable. They can be shaped. You can either shape it into a sheet or can be shaped into a rod. So they are malleable and ductile. The opposite of that is being brittle for nanometals. Nanometals are brittle. They are brittle. Brittle means when you hit it, instead of spreading out the way metals were doing, it shatters. The particle just breaks into so many pieces without any order. So we say the particle is brittle. Maybe if you can get a piece of charcoal. Charcoal is carbon, which is a nanometal. If you can get it nearby, you can try. When you hit it, it will just shatter out, not being shaped into anything like what we saw for metals. So you can say these ones are malleable and ductile, that is, can be shaped, but the nanometals are brittle. Then lastly, we can mention here the issue of the naming. We can say a good number of metals have their name ending up in UM, but remember I said this is not a good way of identifying metals, but nanometals do not have. However, we at least have these two, that is helium and selenium, which have their last two letters looking like that of metals. I repeat, this is not the best way to identify metals and nanometals using the name. So that is question number 1, where we have identified the properties of metals and nanometals and related them in terms of a T table, where I've said you have always to be matching. Don't say an example of metals have a higher boiling point, melting and boiling point, while nanometals are poor conductors of an electric current. Though the statements are correct, but they are not in line, it is not acceptable that way. They all have to match. Question 2, complete the table by giving the name and the symbol of any of 10 metals and nanometals you know of. So we identify 10, or we can talk about 5 elements, metals, 5 elements, nanometals. Write their names and also write their symbols. I can pick on those that are ending with the UM because they are metals. So I can talk of sodium, can talk of potassium. They are ending with the UM, but I can also add there those that do not have such, like copper, can have iron, can have even platinum, these are 5 metals, symbols being sodium, remember the shape, potassium capital K, copper capital C small u, iron capital F small e. Be very careful with the F because we commonly make mistakes by starting it that way. That makes it small letter F. So it must always be capital letter F. Platinum, we have it capital P small t. Nanometals, we can have oxygen, we have hydrogen, we have nitrogen, we have carbon, and lastly can have helium. Should pick at least one with the UM. So using this UM, you can see it's not always a guarantee that these are nanometals and these are metals using that name. The symbol being oxygen. Atomic oxygen is written this way. Molecular oxygen is what we write this way. But what we are talking about here is atomic oxygen, hydrogen, atomic hydrogen, nitrogen, atomic nitrogen. Avoid this case of writing nitrogen this way. This one is wrong. Nitrogen has sharp corners. Carbon, capital C, helium, capital H, small e. So that's our question 2. You can add on as many as you may wish in terms of metals and non-metals. Question 3, this is a statement-based question where I will expect you to fill in some missing links or statements or words. Metals are malleable and ductile. What do each of these terms mean? What do we mean by being malleable and being ductile? Being malleable means it can be shaped into sheets, and being ductile means it can be shaped into a rod. So all in all, they mean shaping. But shaping into what? Are you looking for a rod or looking for a sheet like a piece of paper? So malleable sheet and ductile means being a rod. Another question, what term means the opposite of both malleable and ductile? What can you use to describe the opposite? And that is the property the nanometals give. The opposite of being malleable or the opposite of being ductile, and that is the opposite of being shaped when hit, and that is being brittle. For a substance that cannot be shaped, then it means it's brittle. When you hit to shape, instead of being shaped, it breaks without warning. We say that is a brittle thing. A good example, if you can get a piece of glass, go out with a stone, hit it and see, can it be shaped? No, it can't. Go out, try at your own free time. Then we can say glass is a brittle substance, the opposite of ductile and malleable. Another question is, imagine that, this is a statement, imagine that scientists have discovered a new element. Just a new element has just been discovered. Instead of now 118, we want to have 119. And the new element has been called branium. The new element has been called branium. The new element has been called branium. The question is, predict whether branium is a metal or a nanometal. So they want us to use the name to identify this element as a metal or a nanometal. This one, you will always go with the prediction of how the others look like. Looking at what we saw in terms of identifying metals using the name, we looked at the last two letters, U and M. And what did we say? A name that carries U and M at the end, a majority of those names are for metals. Sodium, potassium, platinum, calcium, magnesium, and so on. So because of that, we can easily predict this one to be a metal, and we say the 119th element that has just been discovered is a metal, and reason being the last letter is UM and not a nanometal. Another question is, on what Okay, yeah, that's just an explanation. On what basis are you looking at this name to be for a metal and not an nonmetal? The basis is on the name, the last two letters of the name being UM. Our last question is, how could you confirm your prediction? How could you confirm your prediction? Yes, you have predicted this element could be a metal. You have answered the next question, that on what basis? And that is UM. But now the last question is, how could you confirm your prediction? Confirm your prediction. Confirming here is go and do a test on the newfound element. The test is you are checking on the properties it is going to give you. Let's go back to our table, the one we have just filled, looking at the properties of metals and nonmetal. It will tell us that if this element will, for example, conduct an electric current, tick, it is agreeing with the metals. But remember, also we had an nonmetal that does that, and that was carbon. Probably that is an example of an nonmetal that has the same property like carbon. So we move on to another one. Does it conduct heat? If yes, then confirmed that this is a metal, and while the other one, as we know for nanometals, do not conduct heat energy. You can also look at the other properties, like if the surface is freshly cut, how does it look like? Is it shiny? Though it's always not a guarantee that if it is shiny, then it confirms it's a metal, because you remember I said that iodine and silicon also have some characteristics by appearance like a metal, while copper and gold have their own way of appearance. Gold is goldenish, it's not shiny as we have described for the other metals. Looking at the melting point, you can, if you find that the melting point is so high, and that is it is existing in solid state, and the melting point is so high, then it also confirms that the material or the substance we are talking about is a metal. So we have been talking about, in general, metals and nonmetals as elements which are found in the periodic table, and these elements, when combined together, same type or different types of elements will lead to formation of compounds, and these compounds are the substances we always encounter in our daily lives. These substances have different properties, as we have seen. That marks the end of our lesson today. Thank you.